We're just going to go ahead and hit record and put that plays there. I think we're back in this. So
Recording again.
Very good. So we need f prime of 0, f prime of x by the power and chain rule is 1/3 times 1 plus x to the negative 2/3. So f prime of 0, 1/3 times 1 plus 0 to the negative 2/3, which is 1/3 times 1 to the negative 2/3. And although the negative 2/3 power is a slightly strange animal, it is 1 over the cube root of 1 squared. 1 raised to any power is going to be 1. So I don't need to worry about that. It's just 1/3. Because 1 raised to any power is 1. So my slope is 1/3. My point is 0, 1. The tangent line is y minus 1 equals 1/3 times x minus 0. Which we can rewrite as y equals 1/3 x plus 1. And that means this thing is L of x. And then we remember from our discussion on Wednesday that f of x is pretty close to L of x as long as we stay close to this base point. I would argue that 1.1 is not close to that base point, and then ask, is that going to be a problem for us? Right, my goal is to approximate the cube root of 1.1, but I'm building my linear approximation at 0, and 1.1 is 1.1 away from 0. That's not close in the sense that we've been talking about, right? Close, we've been talking about here is like, being 0.1 away or 0.01 away, something like that. Not this relatively wide gap of over 1 unit away. So is that a problem? Let me ask the question another way. What input should I be using for x in the original function f to get the cube root of 1.1?
0.1.
Very good. Very good. Because f of x is not the cube root of x. It's the cube root of 1 plus x. So the value of x I'm going to be plugging in to get this approximation is not 1.1, it's 0.1, which is reasonably close to 0. That I am not worried about at all. So here we'd say the cube root. So our second step, right, rewrite this as the linearization. The cube root of 1.1 is exactly equal to f of 0.1. Not f of 1.1, because f of x is not the cube root of x, it's the cube root of 1 plus x. And this is that sneaky trick that I alluded to a little bit last time, but we didn't get to see a concrete example. The number I'm trying to approximate comes from plugging not this in for x, but 0.1 in for x, because the function I'm using isn't the cube root of x, it's the cube root of 1 plus x. So if you use 0.1 for x here, this is 1 plus 0.1, which is 1.1. And 0.1 is close enough to 0, my base point, that I'm not worried about that. That's good. So this is approximately equal to L of 0.1. And that was kind of the big result from last time, that f of some shit is really close to L of that shit, as long as that shit is close to A. And L of that shit is this. So plugged in. And probably what I would do here is rewrite 0.1 as 1/10. That's 1/30th plus 1. Or if you like, 31/30ths. So it's a nice rational approximation for the cube root of 1.1, which is certainly an irrational number. You could carry out the long division. You're going to get a repeating decimal there, and that's okay. But the idea is that this tells you about how far off the cube root of 1.1 is from the cube root of 1. Right? One of the ways you can interpret this answer, especially when written in this form, is that this guy right here is the cube root of 1, right? Cube root of 1 is 1. When we increase the input by 1/10 to the cube root of 1.1, the output increases by about 1/30. Make sense? So this would be our answer. Okay. They also asked us to approximate the cube root of 0.95. That's the answer for part A. The answer for part B, 0.95. And again, here we need to think, let's see if I can get this on the page. We need to think about what value of the function f, I'll just rewrite it. What value of the function f corresponds to this guy? So f of x is the cube root of 1 plus x. So the cube root of 0.95 is f of what?
Would it be negative 0.05?
Yeah, exactly. Negative 0.05. Yep. And then again, this is pretty friggin' close to 0, right? So this is a valid number to play this game with. You can say that is approximately L of negative 0.05. And if you're wondering, if it doesn't jump out at you right away, the thing you would do is just set the thing inside the cube root here equal to the thing inside the cube root here. And that would be a concrete way to say what x value we want to plug in. I want the cube root of 1 plus x to be equal to the cube root of 0.95. So 1 plus x has to be 0.95. Solve that and get negative 0.05. Plugging into the formula for L of x that we cooked up, 1/3 x plus 1. This is 1/3 times negative 0.05 plus 1. And again, I would probably just write this as a fraction. 0.05 is 5/100ths or 1/20th. That's 1/3 times plus 1. And then 1/3 times negative 1/20th is negative 1/60th. And we could write this as a single fraction if we want. (59 over 60). This one is 60 over 60. Cool. So the linear approximation section, I think this is sort of the only subtlety that I'm going to require you guys to navigate, is sometimes the function you're using to approximate isn't the first thought, right? If you're asking me to approximate cube roots of numbers, my first thought would probably be to use f of x equals the cube root of x. But if you're told to use a different function, like the cube root of 1 plus x, then at this last step where you go to plug into your linearization, you do need to think for a minute first about what value of x in the original function corresponds to the number you're trying to approximate. Okay. Section 4.1 is all about mins and maxes. And really there's a handful of tools in here that are built around finding the absolute max for a function under certain conditions. So that function is a continuous function and it's been restricted to a closed bounded interval. We call it a compact set. Before I introduce the theorems there, I don't, like I said, get too far ahead of myself. I want a quick recap on local min, local max, absolute min, absolute max. Make sure we're comfortable with what those things mean. And then to look at some kind of liminal cases, some situations where you might think there's a max, but there isn't, things like that. So let me just say recall that an absolute max for the function f is the largest output from f anywhere on its domain. Or in terms of the graph, it's the tallest point anywhere on the graph. And an absolute min for f is the lowest output anywhere on its domain. So if I have a function that does something like this, and then something like this, and then goes up, and this point right here is like 5, comma, -3. Then I would say the absolute min for f is -3 and occurs when x is equal to 5. This right here would be absolute min. generally the input value is referred to as the location of the min, and the output is the value of the min. And it's important that we have those two things separate and clear in our head. So if I'm asking you, what is the max? That's the y value. If I'm asking you, where is the max? That's the x value. If I ask you, what is the min? Here, the min is -3, the y value. If I ask you, where is the min? The min is located at x equals 5. Part of the reason the definition of a function is the way it is, like every input goes to only one output, is so I can tell you what point you're at on the graph just by specifying an input. I'm going to draw a similar picture for maxes. So here, I might say, this is g of x. The absolute max for g. Is 3. And it's located at x equals 2. So just that language can be an important thing or a bit of a barrier, right? It's often tempting to just report the ordered pair and say this is the absolute min, like -3, 5, or 2, 3 is the absolute max. And if you do that, I'll assuming everything else is correct, I'll give you credit for the procedure up to that. But there are questions that are phrased in such a way to just make sure that you're comfy with this, especially like true, false, multiple choice type questions. So I want you to be aware of the vocabulary. Another term for absolute in this context is global. You'll see sometimes the word global max or global min. That means the same thing as absolute max or absolute min. So you might want to make a little note. Absolute and global mean the same thing. I may slip from time to time and interchange the words, but I'll do my best to always refer to these using consistent language, so absolute. Local extrema are the same sort of thing, but instead of everywhere on the domain, we just mean nearby. So if you zoom in and that point looks like it would be an absolute max, if that blue window was the whole domain, then that's a local max. Local min. Actually, let me phrase this slightly differently. The function has a local min at x equals a means that f of x is greater than f of a for all x near a. And your textbook, what are we using? We're using Stewart now. Yeah, no, they get this right. Okay. Yeah, the pre-calc text gets this wrong. They use a weak inequality there, which would be wrong. And then we say that the function has a local max x equals a if f of x is less than f of a. Near a. And there's a fudge word in each of these sentences. That's the word near. What does nearby mean? And it's similar to in the linear approximation section where we talk about, keeping x near a in order for that linear approximation to be valid. In this context, what it means is there's an open interval centered at a such that that inequality is true for all x's within that interval. Intuitively, if you have the graph, this is not a hard thing. That's something like this. So kind of what we mean by near here is that it's possible to put a little open interval around A such that if you focus your attention just to that window, everywhere in that window, the y value on the graph is bigger than it is there. Or here, it's possible to put a little window about B such that the y values on the graph are lower than the y value at that point. So these would all be local extrema. The word for mins and maxes together is extreme. And kind of the way I think of it is if you ignore everything else and just look here, is this a global min? If I was to delete everything out, there it is, right? Global instead of absolute. If you ignore everything else except for the stuff that's in this window, is that an absolute min? If this was the whole graph, just this thing, then yeah, that would be an absolute min. It's the lowest point on the graph anywhere. Okay, well then it is a local min for the whole picture, for the whole function. Same thing for local max. If I were to look and pretend like this is the whole function, that would be an absolute max. Well, it's not the whole function, but that means that this point right here is a local max. And the language is the same. We would say there's a local max at x equals b, and the max value is whatever the y value is here. So there's a local max at x equals b. I don't know what the max value is here because I didn't tell you what the y value is. There are local mins at x equals a. C. I know that you've seen this before in algebra classes, but now that you have the benefit of knowing some calculus, you might recognize that these points have a tendency to show up at places where tangent lines are horizontal, right? If I was to draw the tangent line to this function right here at x equals b, that tangent would be a horizontal tangent. If I were to draw the tangent line down here at x equals a, that would be a horizontal tangent. Same is true here. The tangent would be horizontal. And that's one tool we're going to have to hunt for local maxes and local mins. But that's actually not the purpose or the main point of section 4.1. We're going to talk about that stuff in 4.2. In 4.1, the real goal here is to find how to discover how to find absolute extrema. So we are presented with a handful of theorems in 4.1, and I want to go through them in the order the textbook does. So let's take a look at the order the book introduces these things. Local min, local max, same pictures we've got. Right. Yeah, I suppose there are some notes we should make, right? A point can be both a local min and a local max. Sorry, can be both a local min and absolute min. Let me see, do they introduce the theorem? Yeah, okay. Yes, you are. Yes. In fact, the example of the sine function they gave there, let's put that in our notes. That's not bad. So, no. It is possible to have multiple local extrema. And extrema is just the word for mins and maxes together. Another note. A point can be both a local min or max and absolute min or max. And the example they use of the sine function is a perfectly fine one. And of course, it continues over here. So each one of these is a local max. Sine has infinitely many local maxes. Each one of these is a local min. So not only can you have several of each, you can have infinitely many of each, right? Because this function is periodic, he does this forever and ever, amen. Right, there would be another local max coming up over here. It's also true that each of these is an absolute max and an absolute min. So each one of these is an abs and local max. Each one of the lower guys is an absolute and local min. Okay. Let's look at, there's one other little subtle point here, and that's that, and not every textbook takes this position, but your textbook takes the position that an endpoint, if you have a function whose domain is a finite interval, endpoints can't be local extremely. And not everybody agrees with this. I don't agree with this, but our book takes the position that endpoints, and I'll elaborate with a picture on what I mean by endpoints, can't be local extremely. Because kind of the idea is that there needs to be an open interval centered at that point, at that x value, such that that inequality is true. You cannot center an open interval at an endpoint because the domain doesn't extend to that other side. So let's illustrate. This is a little bit contrary to the intuition that if you like put a little window around it, that's an absolute min, right? Well, it's an absolute min anyway. But your book would say this is an absolute min, but it's not a local min. Not a local min because it's an endpoint. The function does not continue over here at all. So I cannot talk about a little window centered at A where I can compare the height of the function on either side. So we would identify, I'll draw over here because this is easier. This would be an absolute max, but not a local max. Because it is an end point. And the same thing going on over there at A. That would be an absolute min, but not a local min because it's an endpoint. Now, if you apply the standard inequality definition, you'll see that they would actually meet that definition, but I'm not going to argue with James Stewart. You guys kind of understand what I mean when I'm saying this? What we're talking about here? I don't think it'll cause you any major conceptual hurdles, but it can be very frustrating in the homework when they ask you to identify all the local mins and you keep clicking this point because like, duh, that looks like a local min. Oh, but it's at an endpoint, so they don't want me to include that. When we talk about mins and maxes in college algebra, it's always very simple, hills and valleys. When we talk about mins and maxes in pre-calculus, oftentimes we try to get a little bit more brave by looking at things like piecewise functions and functions with restricted domains. And now that we're here in calculus where the topic truly belongs, we need to be extremely careful about open versus closed. So I drew both of these with closed points, and I did that on purpose. We can add the note over here. This would be an abs min, but not local because it's end. So the idea is that the domain of this function is the closed interval from A to B. And because I cannot compare this max value with the value of the function anywhere to the right of B, I can't really proclaim it to be local because there is no open interval centered at B where I can play that game. And there are perfectly reasonable formal ways around this. I'll stop harping on it. I'll just leave it there. It's a pet peeve. Let's identify the location of any extrema for the function f graphed below. I'll call this -2, +1, +4. Like so. Give me 1 second, guys. Yep. All right. Okay. Yeah, that was weird. I'm not sure why, but for one reason or another, Zoom just decided to boot me out. Looks like we're back though. So we were trying to identify the location of any extrema for the function f graphed below. So this is the graph y equals f of x. This horizontal axis is the x-axis. And we got ourselves a pretty wonky looking thing here. When I say we need to be very careful about open and closed points, this is an example of a function where you want to think quite carefully about which is the point on the graph at any of these x values where something interesting is happening. Now, outside of those kind of points where things are being glued together, there are no local or absolute extrema because the function is like constant or monotone, always increasing or always decreasing. So let's start over here at -2. My function's cruising in here, is constant, constant, constant. And then there's this sudden jump up. And then we're cruising back down. What would you say is going on at -2?
So the top one's a local max.
Yeah, yeah, this point right here is a local max. That's correct. So here's how I want to encourage you to think about it. The first step is to ask yourself, well, what is the point on the graph? Our brains are often drawn to things like this, or things like this, or things like this. But remember what the open circle indicates. It indicates that there's not actually a point on the graph there. In order for this to be a function, there can only be one point on the graph at each x value. So even though, for example, over here at 1, it looks like there might be 3 different candidates for an output, only one of them is actually a point on the graph. The open circles indicate that the graph continues over here, but it stops just short of 1, doesn't actually get to 1. And the same thing's true over here. So the only point on the graph here is this guy. And similarly, at -2, the only point that's actually on this graph whose x value is -2 is this filled in point right here. And if you draw a little window around the graph there, that is the tallest point anywhere in that window. So that would be a local max.
Isn't that an endpoint though?
I understand what you're thinking, but no. So the idea of an endpoint is if there's nothing to compare it against on the other side, then that's an endpoint. So the reason these were endpoints is because this interval AB was the whole domain.
Okay, that makes sense because it keeps going.
Yeah, so there is stuff to compare to on both sides. So that's not technically an endpoint. It's a little bit finicky, right?
What if from -2, like there was no direction, like there was no arrow there, like it was just
yeah, then this is no longer a local max, which is not satisfying, is it? But that would be correct. That is the stance that is taken in our book. Now this still would be something else, and there is still something else we should add to this answer. What else do you notice about this point?
It's an absolute max.
Yeah, there's nothing above it anywhere. This is also an absolute max. This is both an absolute and local max. Is there anything going on down here at this point?
No.
Very good. Yeah, that's bait. That's total bait, right? There's nothing going on there. There ain't even a point on the graph there. Remember, that's that open circle. It means that there's not even a point on the graph there. So in order for a point to be a min or a max, it has to be a point on the graph. And that is not a point on the graph. All right, nothing interesting. So going right to left, nothing interesting. Oh, here's an absolute and local max. Nothing interesting, nothing interesting. Something definitely funky going on here. What's going on here?
It's just one point.
Yep, there's only one point on the graph there. There's no point here. There's no point here. So the only point we're interested in is this one. The only point to say anything about at x equals 1 is this, because that's the only point on the graph at x equals 1. So if you had to compare the size of the output, the y value, at x equals 1 to the other y values on the graph nearby, what would you say about that?
It's a local max.
Good. It's a local max, right? Within this blue window that I've highlighted here, this is the tallest point. So this is a local max. It doesn't look how we're used to seeing local maxes look, right? It's not the top of a hill. And it's not even connected to any part of a curve, but it is still a local max because whatever this output is here, say 3, or 10, or whatever, that's bigger than any of the outputs within the window when you draw a little window around it. So if you can draw a window around that point, and that is the tallest point in that window, if there exists any window, no matter how narrow, which makes that true, then that point's a local max. Okay, the next place of interest is over here at 4. What's going on at 4?
It's an absolute min and a local min.
Very good. Yeah, and almost. You got me on that too, because I wasn't intending it, and then I was like, oh yeah, it is. It is a local min. That is true, right? So if I put a window around 4, then that is the lowest point anywhere in that window. So this is a local min. But it's not an absolute min because there are points on the graph over here, right? Which are lower. So that is a local min, but it's not an absolute min. We haven't quite answered the question though. The question said, identify the location of any extrema. And remember, location means the x value. So I want to list each type of extrema that can exist. Absolute max, absolute min, local max, local min. There was an absolute max and it occurred at x equals -2. That's the location of the absolute max. Remember, it's always the input. There was no absolute min. We did have a local max. We had 2 local maxes. One was at -2 and another was at +1. And there was one local min and it was at x equals 4.
And you said because the graph extends below the x-axis, there is no absolute min, correct?
Yeah, and that would be a correct way to argue. If we wanted to be even more precise, we could say because the graph extends below this point. So this point would be a candidate for an absolute min if there was no part of the graph that went below it. Why is there not an absolute min? Isn't that weird? Because here's lots of parts of the graph that go below this local min. Why isn't there a local min? Isn't that strange? Or sorry, why isn't there an absolute min? Isn't that strange?
Because there's a discontinuity.
Oh, could you say that one more time for me, Robbie?
Because there's no defined point like our camera said.
Yeah, that's the idea. That's the idea. So what we're kind of what I'm trying to get at is that often we're used to this idea that either the graph goes down forever, right? There's some place where the graph goes down to -infinity, or there is a local min, absolute min. Either the graph goes down forever or there is an absolute min. But here we have a graph whose range is still finite, right? This guy does not go down to -infinity ever, but there's also no lowest point. And the subtle thing that's going on there is that as you walk along the graph towards this open circle, you go lower and lower and lower and lower, but you never reach a lowest point. When you get to -1, you immediately ping up here to this local max. So the y values down here, they will get small and they will approach whatever the y value of this point is. In other words, the range of this function is an open interval, open on the bottom at least. Whatever this number is, whatever that y value is there, it's not in the range. So it is possible, even though you have a finite range, for there to not be a smallest element of the range. And that's this idea of open intervals, right? So the range here is an interval, but it's open on the bottom, closed on the top, open on the bottom. Okay. So I suppose I should go ahead and introduce the theorem to you now. The main theorem in 4.1, and this is where we'll pick it back up on Monday. I think they just call this the extreme value theorem. They don't give it its proper name. This is, do we do Fermat's theorem in here? Yeah, they do. Okay, good. That graph we were just looking at kind of illustrates one of the ways this theorem can fail. So every time you look at a theorem, you should ask, what happens if I take away some of the hypotheses? Theorems are usually phrased as, if this is true, then this is true. The first chunk of things are the hypotheses. It says, if f is a continuous function on a closed interval a comma b, then f attains both an absolute min and an absolute max on AB. The big boy version of this theorem in our real analysis class or advanced calc class says that continuous functions on compact sets attain mins and maxes, or a little more advanced would be the continuous image of a compact set is another compact set. The idea is that continuous functions respect topology. Topology is the open or closedness of an interval, right? For us, that's a fine way to think of it. So if I wanted to say this is a closed interval, I'm saying that's the topology of the interval. An open interval, open is the topology of the interval. Continuous functions, if you apply them to a closed set, spit out another closed set, which means that the image of this, or the range, if you like, is another closed interval, which means it's got a largest element, and that largest element is a part of the set, a part of the range. And it's got a smallest element, and that smallest element is a part of the set, a part of the range. So that largest element, that would be your absolute max, the largest element of the range, largest y value. And the smallest element of that range would be the smallest y value, your absolute min. Ways this can break asymptotes, right? Failing to be continuous in all sorts of different ways. This is not continuous on AB. So while it does have an absolute min right here, it does not have an absolute max. Or you can have really weird jump behavior. But if you require your function to be continuous, then no matter what you do, that's not going to be a function. No matter what you do, there's going to be a tallest point and a lowest point. So this is continuous. I'll pretend like I didn't violate the definition of a function right here briefly. This is continuous on AB, the closed interval AB. So we do end up with an absolute max and an absolute min. Here we had an absolute min, but no absolute max. The main goal of section 4.1 is to identify the absolute max for a continuous function given a closed bounded interval. And those can occur one of two ways, right? The absolute max can occur as an endpoint, as it did here. And the absolute min could occur as an endpoint or as something like this in the interior of the domain. The other big theorem in 4.1 this is called Fermat's theorem. Fermat, by the way, Pierre de Fermat, have you guys heard of this guy? A French mathematician. He was alive hundreds of years ago. I'm not sure exactly. I want to say around the time of the Renaissance, before the French Revolution, I'm pretty sure. After Newton, for sure. But somewhere 14, 15, 1600s. I know that's a big range, but anyway, Pierre de Fermat was a French lawyer who was into mathematics on the side. It was his hobby. And he would, because he was wealthy enough to just sit around and worry about math in his spare time when he wasn't lawyering, he would make conjectures, come up with ideas that he thought were true. And he was certainly a genius, but a little bit short on mathematical training. So many of his conjectures he either didn't prove or he wrote flawed proofs of and claimed they were true. Because he never tried to publish anything, nobody really cared. Until many, many years later, when people discovered one of his old journals where he said, I have this beautiful theorem. And this has nothing to do with this class, so you don't need to put this in your notes. I'm going to put on some crumpled scratch paper here. That said, the equation x to the n plus y to the n equals z to the n has no whole number solutions if n is greater than 2. We know that if n is equal to 2, there are lots of whole numbered solutions. They're called Pythagorean triples, right? Like think back your 3, 4, 5 triangles, 3 squared plus 4 squared equals 5 squared. There's lots of others too. There's infinitely many Pythagorean triples. But if you make this power 3, like x cubed plus y cubed equals z cubed, no whole number solutions. If this power is 4 or 5 or 6, no whole number solutions. Pierre de Fermat conjectured this back when he was alive, and it remained an open problem until Andrew Wiles proved it in 1996 using some extremely advanced, algebraic geometry. Fermat claimed to have a proof. If you read in his journal, he says, I found a most beautiful proof of this theorem. Sadly, it doesn't quite fit in the little bit of space I have left on the page, so I'm just not going to write it down. Like a dick, right? And And for hundreds of years, mathematicians searched for a proof, and no elementary proof is known to exist yet. So almost sure Fermat either didn't have a proof and was just fucking with us, or whatever proof he had was flawed in some way. But Andrew Wiles did finally prove it by connecting elliptic curves to these things called modular forms. Anyway, the same guy had another conjecture, turned out to be true, called Fermat's theorem. And this says, if f is differentiable at x equals a and has either a local min or local max at x equals a, then f primed of a must be 0. And this is that thing I alluded to at the start when we were talking about horizontal tangent lines kind of matching up with where you have local mins and local maxes. There are lots of ways to have local mins and local maxes without having a horizontal tangent line. We saw that in the example before, right? Where the lots of holes and jumps and stuff. But those functions all fail to be continuous and therefore fail to be differentiable at that point. But if you have a nice smooth curve, or at least the curve is smooth at that x value, where you have a min or a max, then the derivative has to be 0, has to be 0. So what all of this is getting at is a kind of procedure for hunting down absolute mins and absolute maxes. Because an absolute min or max is either going to be a local min or max, or it's going to be an endpoint. So if you take a nice, not just continuous, but differentiable function, and you restrict it to a closed interval, then you can go hunting for the absolute min or absolute max by looking for all the places where the tangent line is horizontal, and then comparing the y values at those points to the y values at the endpoints of the interval. Whichever one of those is largest must be your absolute max, because if the function is smooth and the absolute min, say, occurs in here as one of these valleys, then you'll detect that with Fermat's theorem by finding the solution to f prime equals 0. And the only other possibility, since this function is smooth, is that the absolute min or absolute max occurred as an endpoint. And you'll detect that by checking the endpoints. I want to leave a little bit of 4.1 for us to talk about on Monday. So I am going to go ahead and stop here. On Monday, I will outline that algorithm to hunt for the absolute min and absolute max of a function. We'll go back over these theorems in brief, but I won't spend as much time drawing pictures. And then we will solve some problems. That'll go quite quickly. So on Monday, also expect us to go through 4.2, which is where we're going to start talking about figuring out where a function is increasing and decreasing by making arguments with its derivative. And that's something that, again, you can probably kind of smell coming from the stuff we've done in the past. But this is where I will leave it. We're building up to a place where we'll be able to graph a function very nicely by hand without a graphing calculator, anything like that. And not just using transformations, not just sliding stuff around or flipping it and stretching it, but genuinely functions that we don't know anything about. We will be able to find where they're increasing and decreasing, find where they have mins and maxes, find where this thing called points of inflection live. And from all of that, we will be able to draw quite a lovely graph. So that's where we're going. Any questions for me before I let you guys go for the day?
Hello?
Yeah, Eric.
Just to be real clear real quick. So when you say absolute max, you mean for the whole entirety of the function?
Yep. Yeah, and in the context of this theorem, the entirety of the function is the interval AB. So even if this function's natural domain is all real numbers, then if we're talking about restricting that function to a closed bounded interval. But yeah, absolute max means the tallest point anywhere on the graph. Alrighty then, I will go ahead and end the meeting here. We'll play around with lots of examples on Monday, and that's it. Make sure you work out that homework. Pay careful attention to the related rates problems. Those tend to be a bit tricky. If you feel at all uncomfortable with them, shoot me a Canvas message and email. I can send you some videos, worked examples, extra stuff. The more you practice, the better off you will be, I promise. And then on Monday, we'll go hunting for mins and maxes together. Take care, guys.